Alright, today we'll be looking at something called direct proportion, and we'll start by imagining three different scenarios. So first, you're running at some constant speed, and in 3 seconds you've run 15 meters, say. The second one, you've got an endless supply of large identical coconuts, and you find that, say, these 4 coconuts weigh 10 kilograms. And third, as of making this video, 10 Australian dollars is equal to 7.6 US dollars. So what's the same in all these scenarios? Well, first, they don't really respect addition. What do we mean by that? In the first scenario, if we add 1 extra second, so we're adding a second, well, clearly we haven't just run 1 extra meter. So you can't just add 1 to both the time and the distance. You might be able to see just by dividing those numbers that we're actually able to run 5 meters each second. So by the 4-second mark, we've actually run 20 meters, not like 16 or something. In the second scenario, if we add 1 extra coconut, clearly that's not just 1 extra kilogram either. Again, by dividing, you'd see that each coconut is actually 2.5 kilos. But more on that later. In the third scenario, well, hopefully you've lived enough life to know that adding 1 Australian dollar isn't quite the same as adding 1 US dollar, because they're worth different values. But what we do have is that in all these situations, we actually respect multiplication. What do we mean by that? Well, back to the top one. If we double the running time, assuming we don't change speed, then our distance will also double from 15 to 30 meters. In the second case, doubling the number of identical coconuts will also double the mass from 10 kilos to 20 kilos. And in the third, doubling the amount of Australian currency you have will also double the amount of US currency you have. See, these all illustrate this proportional relationship, one that sort of respects multiplication in this way. And if we had to write an equation describing all those stories, here's what we'd have. In the first scenario, again, hopefully by dividing, you can see that we're running at 5 meters per second, and that means our distance traveled equals 5 times the time spent running. In the second scenario, we again have that dividing each coconut gives 2.5 kilos for each one, and that means the total mass equals 2.5 times the number of coconuts. And in the third scenario, also by dividing, we would find that each Australian dollar is worth 0.76 US dollars, or 76 cents or whatever. And so that means that the amount of US dollars we have would equal 0.76 times the amount of Australian dollars we have. Now, do you really need these formulas to solve problems with these stories? Hopefully not. Might even make it harder. But annoyingly, we sometimes use language that kind of forces you to write things out in this way. So here's what you need to know. All these formulas follow the same pattern, which is where one quantity is just a constant number multiplied by another quantity, and I've put that number in the blue. So we've got some y equaling some fixed number in the blue box multiplied by x. And that's the most important thing. That blue box number is the same and doesn't change for each story. What that means is for each story, that blue box number will stay constant, while the x and the y can change. Okay, so if 1 coconut is 2.5 kilos, it's always going to stay at that 2.5 for that story, for that question. Okay, and in this case, we say y is directly proportional to x. Now, this form should feel awfully familiar. It's like all that straight line stuff we've been doing. The blue box captures that idea of gradient. I hope you can see that. Okay, not just that it's multiplying by the x, but where did that blue box come from? Well, in the first case, it was how far you can run in 1 meter, or how heavy 1 coconut is, or how many US dollars 1 Australia dollar is worth. And so that's the gradient idea, right? If you go across by 1, how far up does it go? But you may notice that there is no y-intercept. There's no red number that we've been using here. It's like the starting point of these relationships must be 0 for both variables. And it makes sense whenever you're dealing with these direct proportion stories. If I don't run at all, then obviously I've traveled 0 distance. If there are no coconuts, obviously it doesn't weigh anything. And if you're broke in Australian dollars, then you're damn well bankrupt in US dollars as well. Okay, so this type of relationship is what we mean by direct proportion or direct variation. Okay. Now, most problems of this sort you should just be able to do by dividing and multiplying as appropriate, and I hope you can sort of do that in most cases. But again, sometimes the language forces you to set things up in this sort of way. So let's look at an example of that. Okay, so we have in this story, read it if you have to, pause it if you need to, but we have a force F directly proportional to the acceleration A. And we're told that a force of 60 newtons results in an acceleration of 8 meters per second square. And we want a formula relating F with A, and then we need to calculate A when F is 285. So we'll start by writing out this direct proportion relationship. So F equals some blue box fixed number multiplied by A. And whenever we have this, your first step will pretty much always be to find that number in the blue box. Once you have that number, everything else just becomes easy. Okay, so remember that getting that blue box number is the most important thing at this point. How do we do that? Well, we're told that when F is 60, A is 8. So what we can do is replace F with 60 and A with 8 in that equation. Then we get rid of the times 8 by dividing both sides by 8, and so the blue box number is 7.5. And once again, in each story, that blue box number is a constant. So we can rewrite our equation as F equals 7.5 times A, and trust that for the remainder of this question, the remainder of this story, it's going to stay at 7.5. Okay? So now we want to calculate the acceleration A when F equals 285. That's the second part of the question. So we use the same formula, because again, that 7.5 always works in this question. Okay, but this time we know that F is 285. Okay, because remember, F and A can change even if the blue box number must stay constant. And so to find the A now, we can do the same thing, divide both sides by 7.5, giving us 38 as our final answer for that. Okay. So again, with most problems, you should just be able to do it by dividing and multiplying as necessary, but sometimes, like in this question, you'll be forced to use this direct proportion language. So then you'll need to set up the equation with that empty box, use the given information to work out what number goes in the box, then use that formula to work out everything else you need to. Okay, so that's direct proportion. Thanks for watching. I'll see you later.